A chemistry, still smoky in the PNW. All right, so today we're going to talk about the concepts of wetting versus non-wetting substances. And so I'm going to answer once and for all that dumb question that's been all over TikTok and the internet, which is, what is water wet? There is an answer to that. So whatever anyone else tells you, you just say, no, Mr. T told me this. All right, so let's just redefine the definitions before we get into this concept of what does it mean to be wetting or non-wetting. So cohesion is the attraction between like molecules. So water molecules are strongly attracted to each other due to cohesion, and so that's what allows water droplets to stay together. Surface tension is what allows them to bead up against the force of gravity, so they can bead up and form a near spherical droplet. And adhesion is the attraction between dissimilar molecules, and so that's what allows them to stick to the grass blades without running off. All right, so what'd you get on the coin challenge? I'm really curious. Email that over to me. Most people, in my experience running this lab, will get somewhere on the order of 20 to 30 to 40 droplets. I did get someone once with 96. They were very, very careful, and they were smart. They did tiny droplets. Okay, so wetting versus non-wetting. So here are three possible droplets that place on a surface, and let's see what's going on with this. So droplet A is a liquid that contains little adhesion to the surface, and thus we would say it's non-wetting. It's not going to stick to that surface. So they have strong cohesion, so it's sticking to itself to make this near spherical droplet, but it's not attracted to the surface it's on, so it's trying to minimize the surface area that it's in contact with. So non-wetting substances are basically substances who have no attraction, no adhesion to the surface it's on. B is a liquid with moderate adhesion. You'll notice that it still has fairly good cohesion, so it's making this nice dome, but it's also got quite a surface right here on surface area right there. And then letter C is something that has very high adhesion and pretty low cohesion. It's not forming that dome, but it really is attracted to the surface that it's on. We would say that C is definitely wetting the surface. It has high adhesion and it's coating the surface that it's on. So a wetting material is something that has high adhesion and will stick to the surfaces that it's on. A non-wetting substance is something that has low adhesion and does not stick to those surfaces. So let's take a look at a couple of examples. So here's the metal gallium. Now gallium is interesting because it is a metal that melts at about 79 degrees Fahrenheit. In other words, it will melt in your hand. So you could actually take a piece of solid gallium, drop it in a test tube, put your hand around that test tube, and just your body heat will begin to melt it. But gallium also has incredibly high incredibly high adhesion to the glass. So as the gallium melts, it begins coating the glass in a thin layer of liquid gallium. In fact, it's so attracted to the glass, you can't get it off again. No matter how warm you try to heat it up to try to melt it off the glass, it will not come off the glass. It is so stuck to that glass due to high adhesion. On the other hand, here's an example of a non-wetting substance. So in this case, it's water, which typically does wet a lot of things. Water has typically very good adhesion to surfaces, but this water is on a leaf that has a thick waxy cuticle. So it has a non-polar waxy substance on its leaf, and so when the water droplets hit that leaf, they bead up and they roll around without ever sticking to it. So we would say that water is non-wetting to wax. Water may be wetting to glass, but it's non-wetting to wax. And so it really depends on the combination of the two substances. What kind of liquid are you using and what kind of surface is it going on will determine whether it's wetting or non-wetting. So to answer the question about is water wet, well, you have to ask yourself, does water stick to itself? If the surface was water and you added water to it, would the water molecules stick to it? And of course, water has very high cohesion. Water does stick to other water molecules. So the answer is water is in fact wet. In fact, water has the combination of both adhering to itself and to other substances. So it is both wetting to lots of things and it's wet to itself. Hope that answers that TikTok question, because I don't want to talk about it ever again. All right, let's talk about something called capillary action. So capillary action is the ability of a liquid to climb up a surface against the force of gravity. And the higher the level of the adhesion between the substance it's climbing and the substance that is doing the climbing, and the cohesion within that liquid, the more rapidly this capillary action can occur. So if you were to take a glass tube and drop it into some water, you would notice that the water in the tube would be above the level of the water in the container. So you'll notice on here that the water level is above that container. Interestingly, the thinner the tube, the higher the water climbs. And that has to do with increasing the surface area of the glass relative to the volume of water that's in the tube. And so there's less overall weight pulling down that column of water and more surface area for it to cling on to it. In fact, you can actually have tubes that go down into the micron size, and you can actually get water to climb up to about a meter in height above the surface just due to capillary action. That's why water will have a tendency to climb up a paper towel due to capillary action. So the water molecules are attracted to each other, but they're also attracted to the paper molecules. And so as the water molecules are attracted and stick to the paper molecules, they actually drag water molecules behind them due to that strong cohesive force. And then the water molecules that are still moving around will touch the next molecule of paper with that adhesion and pull more water up behind it. And eventually this will go up and wet much of that paper towel. Here's some capillary action in which they've dropped a piece of concrete into a thing of water. After about a half a minute, the water has crept up through the pores of the concrete to this height right here. After 18 minutes, it's crept up even higher. And after 1 hour, it has gone even higher than that. Capillaries, and this idea of capillary action, is really important to biological organisms, including yourself. So you have to deliver oxygen to every single cell in your body. And the delivery mechanism by which oxygen molecules get to your cells is through red blood cells. And the red blood cells travel in your blood vessels. So your heart will beat and push the blood through your arteries, through your blood vessels, on the way to every part of your body. But when you get down to the cellular level, the blood vessels get so tiny that they're so narrow that even only one red blood cell at a time can fit through that tiny, tiny little tube. At that point, the frictional forces of having such a massive surface area and such a tiny blood vessel is so much that the heart itself actually can't push the blood through there. The force of the heart beating is not enough to force blood through your capillaries. But that's okay, because the blood itself will move through the capillaries through capillary action, where the water in your blood is attracted to the vessel walls. They start moving their way down the vessel wall due to capillary action, and then as they move their way down, they pull additional water molecules behind them because of cohesion. Along the way, the red blood cells creep along and then deliver the oxygen to your cells. All right, let's see what's next.